All right, so I'm going to talk about results from my PhD work and then ongoing work I've sort of been doing on the side during my postdoc at Brown. And I left, doesn't come out as a black box on my Mac, but on this one it does. But I actually left this in because I actually took the time to make a new map for this presentation with GMT showing like the sort of key geodynamic features. And I wanted sort of north going up, and then I wanted to actually have one showing the entire plate boundary as well as like the east and west edges. And so from a geodynamics perspective, Alaska is actually quite interesting. And where you see a lateral variation along the strike of the trench in slab age, and then you have a variability in the slab morphology going to flat slab. You have in the upper plate lithospheric heterogeneity, including large-scale faults like the Denali Fault, for example, that had a 7.9 earthquake in the early 2000s. And then in addition, as Ken spoke about, the active collision of the Yakutat Plateau. And so one of the things that, what I'm going to talk about today are just results that we're going after sort of two scientific questions, and then at the end I'll link it back to we're looking ahead for EarthScope. But one of the questions was far-field deformation and mountain building. And so for Alaska, it's located above, has a flat slab, and what's interesting is that although a lot of work in upper plate deformation has focused on like lithospheric heterogeneities and sort of indenters, but in a 2D model that don't actually include the slab. I thought that actually I wanted to see if you put in a slab dynamically, how does that translate into upper plate deformation? And so this is just a plot of apatite fission track from the Central Alaska Range showing a change in slope around 5 MA, indicating active uplift and exhumation. So it's interesting from that perspective. And then there's also interesting geodynamic features in the subsurface. As Jeff mentioned, in the center of oceanic plate, so the figure on the right, you see that the plate motion and mantle flow appear to be aligned based on seismic anisotropy observations. However, if you look on the left, we can see that's not the case. And here's an example from Alaska where you can see the seismic fast axes are spatially variable and indicating complex flow close to a subduction zone. So this is the approach. This isn't necessarily the approach from all geodynamic modelers. My approach tends to be particularly data intensive in terms of the model construction as well as comparing for some of the observations. And I rely heavily actually on seismic constraints. So the EarthScope, I'm really looking forward to see what we're going to find in Alaska. But one of the things is we know that we have a subduction transform boundary in Alaska. If we look on the bottom slides, and so you have a slab edge because the slab continues into the transform boundary in the eastern corner, but it doesn't. But what exactly is that morphology of the slab edge? And so one of the things that I looked at was testing two slab shapes. All these dots, these are relocated earthquake hypocenters from Rachowski and Hansen, and there's a range of data, actually maybe 15 different data sources that I use to make this slab shape. And this is the more conservative one that more closely follows the seismicity, where you have a slab down to 300. And then in this corner beneath the wrangles, it only goes to 100 because you can see it's not seismically active and you don't see much in the tomography either. I also tested a shape where I extended it to 300 kilometers all the way to the transform boundary. So to sort of the workflow overall is there's an integration of a variety of data, making slab shape, plate ages to use a thermal structure and a plate boundary structure. I actually wrote a code during my PhD to then take this information and generate a fully three-dimensional thermal structure of the modern plate configuration, and then that creates a density structure that then is input into the CIG community, the CIG supported codes that come to you, and then that outputs velocity, pressure, strain rate that then you can compare to observations. And so this is what went into constructing the thermal structure, the seafloor ages for the subducting plate. The upper plate, this is surface heat flow, and you can see it's quite spotty throughout Alaska, and so this might be a future point for additional, something to think about. That would be interesting to have additional heat flow data. I went ahead and integrated a variety of observations to make these thermal domains on my upper plate. I'm now using you can also use potentially global seismic models for depth to LAB, and for my current work in Central America, that's what I'm using. I'm using the Lykic and Romanowitz model. But at the time, that wasn't available, so I did this alternate approach. But I imagine that with EarthScope, we're going to be able to better refine the upper plate structure, so that would be really interesting. as geodynamic models have indicated, the upper plate structure is actually important for even flow dynamics as well as upper plate deformation. So this is the 3D like slices through the thermal field that comes out of my code. And here's the flat slab through South Central Alaska. And then these profiles just show I have variable upper plate thicknesses spatially. And so this is sort of the setup. I want to point out that these are large-scale models. They run in high-performance computing centers through an exceed allocation, about 17,000 compute hours per job. So they're big. At least they were at the time I ran them. And then in addition to the initial thermal structure, another thing I wanted to look at was, well, when you have the two plates in the models, they have to, to allow them to slide past one another, you have to somehow prescribe that. It's sort of, we haven't quite figured out in geodynamics how to really get a plate interface to dynamically appear. So one of the ways you can do is just like impose one. And so here's a zoom in through the flat slab where this is the viscosity structure. This is 10 to 17, 1024 Pascal seconds. So this is the cold slab, and this is the upper plate, and here's the interface. So here's something where the plate interface is at 10 to 20 Pascal seconds, and then this is a stronger plate interface that's more coupled. So I can look at how that affects plate speed. And again, these are 3D models, so this is me working in the UC Davis Keck Cave. So just imagine this little bit sort of zoomed in. This yellow thing is the Wadeti-Benioff zone surface, and then the purple is my three-dimensional plate interface. Here's just like a 2D slice through it, but it would extend in 3 dimensions along the surface of the slab and then continue into the transform boundary so that you basically allow it separating the Pacific plate so it can move with respect to North America. And I mentioned about the code I use. These are viscous models, run on hundreds to a little over 1,000 cores now. And so in terms of results, the top row shows results for 3 models of velocity predicted for the Pacific plate. The density structure, again, drives the flow. I don't prescribe velocities in the mantle or on the plate, so those are solution. And so on the top surface, these are predicted velocities for the Pacific plate. The white arrow is observed. On the bottom are mantle flow fields for the same models. So if we look at the top, I guess one thing to point out, the colors are viscosity. So 10 to the 17, 10 to 24 Pascal seconds. And we can just maybe look at these two on the left for a second. So here's the subduction transform boundary. And what you see is that there's actually a weakening effect near the plate boundary that emerges in the upper plate. And then these lines here are the slab shape. And so you can see that in these models, the Pacific plate's being driven just about 5 centimeters per year to the northwest. So it's actually a pretty good fit to what's actually observed. This is the same model with this slab shape that has the shorter piece beneath the wrangles. And in this case, the plate motion is like on the order of 1 centimeter per year, because I'll explain that why like in a couple slides. But basically, the effect of using this, this one has a Newtonian viscosity structure, and this one has this non-Newtonian viscosity structure. And the effect of having the Newtonian one, which is what's commonly used in models, actually leads to slower velocities overall. So whereas these non-Newtonian models, you have this weakening effect, which I'll show you in a couple slides. But anyway, that's the point of this one. This upper row is to show you that in these models, the Pacific plate is being predicted to move on the order of observed plate motions. So on the order of 1 to 5 centimeters per year, which is consistent with which we see from GPS. Now, if we look at the same models and go on the subsurface, we can just focus on this one for a second. Here's where you see the deeper slab edge. You see this toroidal flow around the slab. So as you have your slab subducting, you have this return flow around the edge. And this is for one using a non-Newtonian solution where you have a power law relation between the stress and the strain rate. So you reduce the viscosity so the mantle can flow fast. In this one is the Newtonian solution, so it has a slab edge, but you can see overall the velocity field is muted, is damped, consistent with what we see in the surface with just slower overall velocity fields. The difference between the ones on the right and this one has this 2-tiered slab shape. The one on the right has this slab edge that extends to 300 kilometers all the way to the plate boundary. So what you can see is by having this deeper slab edge all the way to the transform boundary, that moves where the toroidal flow is going to be. So when you look at the seismic anisotropy data, like from that's come out of Cascadia and whatnot, and you say, oh, there's a slab edge, that's got to match the anisotropy. Maybe not, because what these show is that over, you have to have, even though there's an edge, it's worth trying to get the detail right of where the slab edge would be, because that'll significantly affect where the toroidal return flow would be. So that's sort of one thing to take away. And the other thing to take away is that is the speed. And that in these models that use the composite viscosity, if you look at the aeroscale, maybe it's hard to see, these are actually predict mantle flow rates an order of magnitude faster than plate motion, so up to like 80 centimeters per year, close to the slab. So the models that predict this rapid flow around the slab also predict surface plate velocities, which are observed, so they're not inconsistent. Rapid mantle flow is not inconsistent with surface plate motions. And so one of the things that I used for this study, this box is a subset of my model domain. It extends on the order of like almost 1,000 kilometers from here in that direction as well, and on something not quite that far to the north. But at any rate, the point is that this is a subset of my model domain, and even within that subset of the domain, there was a smaller subset of seismic anisotropy data. So this is what would be great for EarthScope, is to continue collecting additional data so that we can really test these geodynamic models like everywhere, because they're making predictions for rapid flow here, but they're also making predictions for no rapid flow here. So if we could get additional anisotropy data over here, that would be quite valuable. But anyway, these were what were available at the time. It's a really great study. I was quite fortunate that this the Christensen and neighbors paper is coming out just about when I was processing these results. And so I did a comparison. We calculated the infinite strain axes and did a comparison to the anisotropy, which is in the blue. And we can follow up about this more. But the take home is that we found that models with the more rapid flow better fit the anisotropy that was sampling in the mantle wedge. And so a question you might have is, like, how can you be having rapid mantle flow but then have surface motions that are moving, an order of magnitude slower in the same model? And that actually comes out of the viscosity structure. So this is a map view. On the left are models with this non-Newtonian rheology, and on the right are models with the Newtonian viscosity. This is looking top down, so you can see the return flow around the slab edge. And then these are cross sections, so you can see this poloidal flow and then this toroidal flow. And so one thing that will jump out at you right away is that, again, in the Newtonian models, the flow fields are damped. And so we'll just, maybe that's kind of what you're most familiar with, maybe, so we'll just look at these first. So you see this, and so here's the viscosity structure through near where the flat slab sort of Denali line. And you can see a strong slab core. This is, again, 10 to 17, 10, 24 Pascal seconds. So you can see a slab core that, that emerges, and then you have a decrease in viscosity with depth, but laterally no viscosity changes. And you can see high strain rate located around the slab and the mantle wedge. In the non-Newtonian viscosity models, where you have this velocity gradient, you have high strain rates around the mantle wedge. And what that leads to in a strain rate dependent viscosity is that then you get this reduction. So you have a lateral reduction in the viscosity, a weakening effect. So you reduce your viscous support of the slab. So that does two things. So if you have, slabs don't go in at the same dip forever. At some point, they're going to steepen. And so when they go through, when they want to steepen, if you imagine a slab steepening in water versus honey, it's going to have much less resistance to steepening in the water versus the honey, say, like the Newtonian model. So you reduce the viscous support of the slab as it wants to steepen, and then that basically allows the slab to pivot more quickly. But another thing it does is it means that the slab has to support more of its own weight because it's not being supported by the mantle, which causes the hinge to fail, which then allows you to have more rapid flow here and slower flow of the surface plate because you have this weakening in the hinge that sort of absorbs this differential motion. And so that's a way that you can, with the viscosity structure, you can reconcile that. And I should point out, this non-Newtonian viscosity structure, that's taking into account laboratory experiments from the dislocation creep deformation mechanism. And that's the same mechanism that actually makes the seismic anisotropy. So this rheology not only is consistent with the anisotropy, but it's also consistent in that you can dynamically weaken the wedge. And so that's interesting. So then it's like, oh, but Alaska has a flat slab, but you're saying you have this decoupling and weakened mantle wedge, so that doesn't really make, but then how can you be driving deformation in South Central Alaska? So that's what I'm going to show you, some surface deformation results. So here is, you can see the slab geometry. This is in gray, so you can see the slab coming in. So there's this Denali fault in this Wrangell block motion, and you can see these yellows are where we have active uplift. And so one of the things that we found is that we find that the flat slab, I'm out of time.
A minute.
Yeah. So the flat slab in Alaska, this is like work that's in revision right now. It's coming out, but that we find that this flat slab alone is not enough to drive deformation in Alaska. We can reproduce several first-order features like a Cook Inlet Basin, uplift in the St. Elias, but the flat slab by itself can't get you uplift in the Central Alaska Range. You need the Denali fault as well, and so both those features are important. And so, looking ahead to Alaska, there's a lot of answers sort of dynamically that these models can address, but then there's a lot that they can't, and there's a handful of other work that that's been done. And so I would say major tectonic questions that you make Alaska a prime target are questions of plateau subduction, far-field deformation, escape tectonics, erosion and mountain building, seismic cycle slip variability, plate mantle coupling questions, subslab mantle wedge flow, slab edge upwellings and volcanism, and then just overall trench curvature and detachment. Alaska's had this long-lived history of subduction, but where's the slab? And why is it curved? Why is the trench curved? And how can this be achieved with these collaborations with geodynamists, geochemists, geologists, rock deformation experimental people? And this could be facilitated, I think, through EarthCube, CIG, exceed computation resources, and the continued data sharing and collection with EarthScope moving to Alaska. But then also, I thought that subduction observatory was neat.